Hey there, geometry students. Welcome to the lesson for 10.5. We're going to talk about different segment lengths in circles with this lesson. There's some new vocabulary. Make sure you know those things by the end of this lesson, and using those extra examples in the book for additional help as always. Let's check out a couple of new theorems in this lesson. Let's start with Theorem 10.15. There's been 15 theorems so far in this chapter. Here's the 15th theorem in this chapter. Draw a, I keep doing that. Nope, I don't want that either. Draw a decent size circle, quarter, $half size, something like that. Find about that big, and draw two chords of the circle that intersect, something like this and this. Let's label those points of intersection. This point right here we're going to call C. This one will be A. This one will be E, where the chords intersect. This one B, and this one D. With this lesson, think of the segments, the pieces of the segment multiplying together to equal the pieces of the other segment multiplying together. It's basically, that's what it comes down to. So EA times EB, pretty cool that this works out. I don't think it's intuitive, but it does work out every time. So yeah, you can prove this. There's ways to prove this. It's beyond what we're going to get into here. But EA times EB is going to equal EC, that piece, times this piece. So this segment, the pieces multiplied together, is going to equal this segment with the pieces multiplied together. So EC times ED. Pretty cool. That always works. So this is that theorem. And let's check out an example where we use that theorem. So here's example 1. How many times am I going to do that? Circle, circle, circle. Draw a circle, decent size. Draw in a couple of chords that intersect. And make your picture look like mine as best you can. Let's call this X right here. Let's call this 9. This is going to be point C. This will be O, U, G, and H. Haha, this lady is coughing over there. I like to make words with my letters. Otherwise, it's too boring. If I don't make words with the letters, it makes it more interesting. So cough. Circle H. Center. That's not actually circle H because it's not the center point. Good point to bring up right there. If it's the center point, then you can call it circle that thing. But this is not the center point necessarily. Here, it's off center a little bit. It's just where the chords are intersecting. How could we set this up without the numbers first? You would say that the pieces of the segments multiplied together in this segment equal the pieces of the segments multiplied together in this other segment, this other chord. So a way to write that would be HC times this one, HU would have to equal HG and HO multiplied together. So I can say HO times HG. And now replace those with the values that are there. So HC, that's X. HU is 18. HO is 12. HG is 9. Now it's a pretty basic algebra problem. Let's just solve this for X. So this is going to be 108, and 18X divide by 18. And your answer falls right into place. X equals 6. This right here, let's write this up there. This was true by Theorem 10.15. So if you had to give a justification for that, that's Theorem 10.15. That's why that works out. Now let's check out Theorems 10.16 and 10.17 and then do a couple more examples from there. So Theorems 10.16 and 10.17 say this. Let's split this up. We can fit this into, or just on one part here. We'll have enough room, plenty of room for that. This will be Theorem 10.16. This one will be Theorem 10.17. And draw a couple of circles. This one I'll put off to the right just a little bit more. Same thing with this one, off to the right just a little bit more. I'm going to use the segment tool here. These ones will be secant lines, so they will go through circle like that. and this one will have a tangent line, tangent segment. Back that up just a little bit. There's a stop right there, that's pretty good, and a secant segment. Okay. So what we just talked about, it's sort of still holding true. These segments, the pieces of the segments, are going to multiply together to equal the other pieces of segments. It definitely holds true straight up with this one. This one, there's a little twist to it with Theorem 10-17. So let's call this E, A, B, C, and D. So again, think of that same idea. It's the pieces of the segment multiplied together in one segment equals the pieces of the segment multiplied together in the other one. That applies directly right here. EA times EB, pieces of the segment multiplied together, equals the other one with the pieces multiplied together, EC times ED. That's what that theorem says. And then this one, let's call this E, let's call this A, let's call this C, let's call that D. What this one says is, well, this one it still works, EC times ED. Pardon me, the pieces of the segment there, EC and ED. This one, though, there's only one piece of the segment, so what we're going to do there, think of the same thought, but think of it multiplied by itself. So EA squared, in other words. That's what that theorem says instead. And let's check out a couple examples. Theorem 10-16, we'll do example 2 with that one. Theorem 10-17, we'll do with the third example. You may recognize this guy from X-Men, some of the X-Men movies. Going to draw a circle like that, and let's draw in two secant lines like this here. So they're crossing through. Give the points some labels like you see here. This is not necessarily going to be drawn to scale. We're going to call this B-E-A-S-N-T. That is Beast right there. One of my favorite guys from X-Men. He's really smart. He's really good at math. Yeah, Beast. Good work. And he's also a very powerful dude. 11, 10, let's call this one 12, and we'll call this one X. Okay, so by Theorem 10-16, how can we set this up? Using just the letters first. If I said you had to use that, multiply the pieces together. AE times EB is going to equal AS times ST. And I needed to stop there. I've been saying this wrong. I'm sorry. AE times the whole thing, the piece, the outside part times the whole thing equals the outside part times the whole thing. That's what I've been intending to say. I've written it down right, I just wasn't saying it right. So the outside part times the whole thing equals the outside part times the whole thing. If we go back to our vocabulary, that is the secant segment, the external segment. The secant segment is the part inside the circle. The tangent segment is the part that would be tangent to the circle. The external segment would be the part outside the circle. Okay, and just to clarify one more thing there, I don't usually use the term secant segment. I just talk about the whole thing and the external part, the outside part. So the secant segment is actually the whole thing, the A to B part, and the external segment is this part. So I had written it down right here, I just wasn't saying it right. So if I messed up your thinking there, let's rethink through this. I'm sorry. I really apologize for that. Occasionally I am apt to make a mistake here and there, so make sure you catch me on that. And if you're noticing any mistakes in these videos, let me know. If you're one of my students, you can get some extra credit. We're pointing those things out. Write it down, write down the time, write down the lesson number, etc. when it happened, and I'd be happy to give you some extra points so that I can make these videos the best they can be. So EA, the external segment, times the secant segment times the whole thing equals EC, the external segment times the whole thing, secant segment ED. So that's what's going on here. Here it is the parts. That's the EA part, it's the EB part. Here it's EC times the ED part for Theorem 10-15. But here it's a little different. It's the outside part times the whole thing equals outside part times the whole thing. Then here it's outside part times the whole thing equals tangent part times itself. So let's apply that to this situation here. We're going to have B, AE, not B, but AE times AB. So external part, external segment times secant segment, the whole thing, equals AS, external part, times whole thing, AT. And now let's set that up based on what we have. What would those values be? You need to be careful here to make sure you plug in the right things. So think about what each one has to be lengthwise. AE is clear, that's 11. AB, not quite as straightforward, but should be pretty straightforward still. Is it 10? No, it's the whole thing. It's from A to B, so that's going to be 11 plus 10. 11 plus 10 would be 21. Let's write it as a 10 plus 11 or 11 plus 10 to start. We'll simplify that. A lot of you will be able to skip this step later on, I would assume. And then AS here would be 12 times AT. It's not x, it's the whole thing. It's 12 plus x. So we have 12 plus x is your AT. Let's simplify this. We have 11 times 21 equals 12 times the quantity 12 plus x. From here it's going to be a matter of distributing. Multiplying this together, you get 231. This would be 144 plus 12x. Subtract 144 from both sides. It leaves you with 87. 87 equals 12x divided by 12. Your answer in this case happens to be not a nice whole number. You could reduce that as a fraction. I decided to just put this one as a decimal though. X equals 7.25. I think that probably makes the most sense in the context of the picture to say that 7.25, not 87 over 12 or whatever that is reduced. What would that be reduced? That would be, divide by 3, divide by 3. We'd have 22. It's not coming to me right now. Oh, it's been a long day. I'm sorry. So if I divide by 3 and 3, I'd have fourths. This divided by 3. Come on. Come on, Mr. Wagner. 29. 29, 29. Because 90 divided by 3 would be 30. So 29 over 4 is the same as 7 and 1/4, which would be the same as 7.25. So that checked in here, that seems to make sense. It seems to be reasonable. Remember, this is not drawn to scale perfectly, so it might not look like it's different or larger or smaller than this one, but it should be if it was drawn to scale. This one times the whole thing should be this one times the whole thing. And that's example 2. That's an example of Theorem 1016 put into practice. And for the last one, let's check out Theorem 1017. We're going to use that on this last one here. Here is a picture of one of the most famous parks in the world, maybe the most famous park in the world in terms of a city park. Not national parks, but city parks at least. One more time, I did it. There we go. Circle. There you go, circle. Make a tangent part to this circle now. I'm going to go really horizontal with this tangent part. Pardon me. This will be 30 X, R, A, K, and P. So we'll spell out park with that. Call this 24 right here from K to R. And so by Theorem 1017, we can use this idea. We can square this part, and it would equal the outside, the external segment part, times the whole part, times the secant segment part. So let's set that equation up. It would be PA squared equals AR times AK. Plugging in the values, a lot of you could do that right away, I would imagine, but put this in the notes for now. You can skip that first step later on. Be 30 squared would equal X times, now this would be X plus 24. That's the whole thing, AK. So this would become 900 equals x times the quantity, x plus 24. We could do that, I think, right here. Let's just distribute that x right here. So we have x squared plus 24x. Does this look familiar at all to you from algebra? Can you solve this just for x? No, it's going to be a little more complicated. Yes, we can solve it for x, but it's not a matter of getting rid of the x squared part. There's no way to do that. You're going to have an x squared term, and you're going to have an x term left over plus this regular number. So we have to go back to something. Pulling back from algebra. Subtract 900. Let's see if this starts to look familiar to you. You're going to have 0 on one side, and then everything else on the other side. So not each problem using 10.7 will look like this. These are the harder types of problems though. So you will have to use this at some point. Expect to have to do this on the test at some point to set up something like this. Now if this was factorable, maybe you remember doing something like this. Don't write this down right now. I'm going to put this in yellow to remind you of that. But maybe you remember doing binomials where you factored it into different parts here and here. It's hard to see those. Let's put that in green instead. Don't write this down. Don't write this down. Just think about this. So you were doing things like this where you had x times x and you were trying to put plus or minus sign here, and you tried different combinations. Maybe you used something like a magic x and said, okay, what adds together or multiplies together to negative 900 and adds to positive 24. You tried some different numbers in there, and on this one you could do that all day long and nothing's going to work. So if it is factorable and you remember how to factor, you can do that. But a fallback, something you can always fall back on, is the quadratic formula. The quadratic formula, what does that say? What is that again? Different color time. So at this point, we're going to say x equals and start to work it out from there. So I want to make a side note off to the side here, different color. We are going to use quadratic formula. And what was that? If you know the tune Pop Goes the Weasel, you can think of it like that. I'm going to sing right now. Deal with it. It's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Right there is the quadratic formula. Maybe you remember that, maybe you don't, but it's something you need to know for this assignment and come test time. So we're going to have 3 steps. Step 1, we've already taken care of. Step 1, this is just in general, how do we use the quadratic formula? When do we use it again? It's when you have this x squared part and an x part, and you can't factor it. So we're going to get one side equal to 0. And again, I want to emphasize that you don't always have to use this. Sometimes you can factor it. Sometimes you won't need to use this. Sometimes the numbers will just line up easier, or they won't require that you use factoring or quadratic formula ideas. You just have to divide and solve for plain old x instead of an x squared piece. So just look at the situation, see what it calls for. If you have this x squared and x part, regular number part, you can't figure out how to factor it, then fall back on this. But just trying to show you what the hardest example, what one of those looks like. I want to do that together with you here. So then you're going to find a, b, and c, which would go into here, the quadratic formula. This should say, let's put x equals there. So x equals negative b. Break it into song once again. Plus or minus the square root of b squared minus 4ac all over 2a. Oh, I'm not going to win any Grammy Awards for that anytime soon, but hey, who knows, maybe. Plug in. So step 3, plug them in and simplify. I get really excited about math sometimes, so I'm going to put exclamation points everywhere. Yes, that's what we want to do. Plug them in and simplify. Get one side equal to 0. Find a, b, and c. What is a, b, and c here? Let's write in the invisible number here in a different color. there's a 1 in front of there. That's going to be your A. The B is going to be this plus 24 part. The C is going to be the minus 900 part. So let's label above there. A, B, and C is 1, positive 24, negative 900. Now it's a matter of plugging things into the quadratic formula correctly. So this would be negative 24 plus or minus the square root of b squared, so 24 squared, minus 4 times a is 1, times c, don't forget your negative signs. If there's a negative sign there, it's times negative 900, all over 2a, all over 2 times 1. If you remember something called completing the square, that's where the quadratic formula comes from. You actually were supposed to learn how to prove completing, or how to prove the quadratic formula is what it is, why it works, where it comes from, using completing the square. I would doubt you remember that from your algebra class, though. Maybe you could prove that to the whole class. I would definitely give you some extra credit if you could just stand up here in front of the whole class and prove it off the top of your head without any notes or anything like that. That would be pretty special. I would love to watch that. All right, this is going to be negative 4 times 1 is still negative 4. Negative 4 times negative 900 would be positive. Negative times a negative would make positive 3600. 4 times 9 is 36. Just add 2 zeros after that. This is all over 2 times 1, which would be 2. So we're going to continue to simplify this. You still have x equals, this will be negative 24 plus or minus. This would be 4,176 all over 2. Keep going with that. So negative 24 plus or minus. Don't forget how to simplify the radicals, how to find simplified radical form. And so we could take this, divide it by perfect squares. You could break it up into the factor tree way. You could break it up into the parts, into all the prime factorization parts like that. But I noticed, I did this before, I figured out that 144 is the biggest perfect square that divides evenly into 4,176. And it goes in there 29 times. So 144 times 29 is the same thing as 4,176. If I say this divided by 2, I'm going to continue this thought. I'm just going to continue it up here. So this would be now x equals negative 24 plus or minus the 144. Let's put that in a different color. Think of this coming out of the square root as a 12. And so you're going to have negative 24 plus or minus 12, radical 29. 29 still inside the square root, all over 12. Now that I've done that, I've got this part divided by 2, and I've got this part divided by 2. I can reduce all of that. Sometimes you won't be able to reduce both parts. You have to be able to reduce both parts, though, to reduce the whole thing. You've got to reduce both parts. So if one of these was odd numbers here or here, I couldn't reduce. But I can because they're both even. That means this will be negative 12 for 24 divided by 2. Negative 24 divided by 2 is negative 12. Plus or minus 12 divided by 2 is 6. So this would be your answer, or possible answers. We go back to the picture, though. Think about it in the context of the problem that we're doing. Negative 12 minus 6 radical 29 wouldn't make any sense, because that would be a negative, and then this would just make it more negative. And to say x equals a negative number, no, can't happen. X is a length. A length cannot be negative in Euclidean geometry here. So we're going to say, therefore, x equals negative 12. We get rid of the minus option. We just have the plus option. Negative 12 plus 6 radical 29. If you type that into a calculator, you do 6 times radical 29 and add that to negative 12, you're going to get 20.31. One more little notation to make in a different color here. Why did we use that positive option and not the negative one? Why do we just use the plus instead of the minus? So here we are using positive solution only since x is a distance. And then put cannot be negative. Let's put that in parentheses there. Can't be negative because of that. And that was some definite algebra review there. Talking about the quadratic formula, you may have to use that. You don't have to use that every single time. Just make sure you plug in your numbers carefully, and at times it may be required to use a quadratic formula because of that. But wanted to show you how to use that once again. We'll probably do one together like this in class as well if you're one of my class members. Don't forget about using those extra examples in your book as you go through and start to tackle these problems. Hope you do well with it. Let me know in class if you have any questions. Thanks, guys.